Welcome back, ladies and gentlemen. In the previous lecture, we attempted to answer the question, why is spatial data so important, looking at technical perspective. In this lecture, we will discuss the answers to the same question. Why is spatial data so important from the perspective of spatial data characteristics and analytics? The next slide shows the outline of the presentation. The following will be discussed. The first law of geography, which is about spatial autocorrelation issue, coordinate system issues on transformation between 3D and 2D space, uncertainty, which is about the fact that spatial data is basically probabilistic, modifiable area unit problem. Different aggregations will make different outcomes in spatial analysis. Dr. Tobler in 1970 stated the first law of geography. Everything is related to everything else, but near things are more related than distant things. This is a fundamental concept of spatial autocorrelation, applicable to all spatial variables. An example is sea surface temperature, for which one might expect a high degree of correlation between measurements taken close together. In the case of elevations, a simplistic interpolation function takes the elevation value of nearest stored location and assigns this to the location that is not stored. Smarter interpolation functions involving more than a single stored value should be preferred. Spatial autocorrelation can be defined as the measure of the degree to which one's object is similar to other nearby objects, so that positive spatial relationship or spatial autocorrelation is assumed reasonable for spatial phenomena. On the contrary, in most statistical analysis, independence of data is generally assumed, so the strong presence of spatial autocorrelations makes spatial analysis complicated. The next issue is coordinate system. There are mainly two ways of representing locations with coordinates: geographic or 2D Cartesian. Geographic is based on 3D. Longitude, lambda, latitude, or phi, and ellipsoidal height with a small h. On the other hand, 2D Cartesian is simply x and y. When you apply any analytics to your spatial data, you have to check the coordinate system in the very first step. Think about a given problem. If you have spatial data with geographic coordinates and the sample distance computation is not an easy task at all. Moreover, there are thousands and thousands different map projections and coordinate systems. So clear understanding of coordinate system is required for advanced spatial data management and analytics. Another important aspect of spatial data is uncertainty. Spatial data is basically measurement and intrinsically prone to error. As a result, any analysis result of spatial data is stochastic. In other words, probabilistic. Stochastic, having a random probability distribution or pattern that may be analyzed statistically but may not be predicted precisely. Let's see the example on the slide. When you see $1,000 on your bank account, it's literally $1,000. and in this case, deterministic. On the other hand, when you have a human trajectory collected by GPS unit, the location XY inevitably has uncertainty. As a result, when you conduct any further analysis with the trajectory, the result is probabilistic. So we have to understand the nature of spatial data and to get used to living with uncertainty in spatial analysis. In this lecture, we have discussed the answers to the question, why is spatial in terms of data characteristics and analytics. Spatial data analysis has quite a few different issues from data science. All right, this is the end of the other lecture. Hopefully you enjoy it and you see you all in the next lecture. If you've not subscribed to my channel, kindly subscribe, comment, share, and like. Thank you very much. All the best.